Hello, everybody. Happy Thursday. Um, I we talked about anti-ultra interracialism again, and I don't hate nobody. Okay, if they're ultra interracialists, well, sucks to be them. But their solution, yeah, they should just divorce. Okay, ethnic man married to a beautiful young white girl, yeah, they should divorce because that marriage is null and void from the get-go. Okay, because in terms of humanological ethics, so all they gotta do is divorce, and the white girl should marry a white guy and make white babies. Okay, until before too late. Okay, so that's all there is to their solution. Okay, we all make mistakes. We all make mistakes. Okay, so yeah, some marriages are mistake. Ultra interracialistic marriage is invalid, immoral marriage. Okay, they should divorce. Okay, like Marco Rubio, Ted Cruz, who else? What have you? Yeah, the Steve Mnuchin and Ivanka Trump, and they should all divorce. Okay, they should just divorce, break up, no long-term relationship. Okay, between ethnic men and beautiful young white girls. We cannot. It's wrong thing to do. All right, so yeah, they should break up, divorce, and that's it. Let the white girls get some good white guy and keep making beautiful white babies. Okay, so that's that. Okay, and so why are we only talking about white race? Because they are endangered species and they are most vulnerable species, and also they are very beautiful race. Okay, and very singular and unique race. Other races are not in danger of uh, extinction, but white races. Okay, so they deserve some special care and special attention from us, Caucasian race. Okay, so that's why we are typically, yeah, anti-ultra interracialism focus on protection and preservation of the white race, Caucasian race. Okay, because they are endangered. All right, so yeah, so that's that. So we go back to abstract algebra later. Okay, so helicopter is vertical lift, but it's kind of slow, right? Because the fan, the propeller, they are kind of horizontal, so that's why it cannot go very fast. Because when helicopter, how can helicopter move forward? It makes this slide angle, this horizontal fan. It makes slide angle so that it can go forward. That's why it's so slow. Okay, so this Americans, they invented this vertical lift, something like V280 or something. The Marine, the one they use in Marine, vertical lift, but this is has these two wings and on either side, right? On either this wing, I guess, of this vertical lift thing. So they lift up vertically, and then this fan they rotate so that now they can go forward. Okay, so that's very cool idea. Yeah, very. Now, but it's very big airplane, vertical lift airplane, right? It doesn't have to be that big. You can use it in one man drone. Okay, so maybe it's not such a good idea to use it in one man drone because we don't want one man drone to be too fast. Okay, because we want to minimize any danger. But okay, how a regular helicopter? Yeah, you can make that two V280 in a small helicopter version. I guess we can do that, right? Yeah. So make it smaller, because it's a good idea. All right. Or in terms of drone, I guess what you can do is one man drone or unmanned drone, like helicopter kind of drone. I guess you can do something like this. So you have this drone, right? Here you have this horizontal fan. It's a bird eye view, right? Horizontal fan, so it's a horizontal fan, so it does this vertical lifting. Now here you have, so when it does the vertical lifting and landing, this vertical unit, they are not doing anything, okay? Maybe they are covered or whatever. But once you lift up in the air, then this guy gradually slow down and this guy take over so that it can move forward very fast, okay? Yeah, this kind of vertical lift drone. Nowadays, drones are just all they have wings, fans, but they're all horizontal, right? So that they all do the vertical thing. The slide angle, that's how they go forward, backward, but it doesn't have to be that way, okay? Yeah, just tweak it a little bit so that, yeah, for vertical lift off, yeah, you just use two of them, and for the going forward, yeah, you turn these two guys off and use these two guys for horizontal. I mean the forward, backward, whatever. Okay. Yeah, you can have as many wings as you can imagine. Okay, you can have like this so that you can go forward and backward, or maybe not here but here, whatever. Right? Yeah, this possibility is endless. Okay, with this drone stuff. Okay, so yeah, Elon Musk, he's fucking moron, right? So he invested on what, driverless car and shit. No, that's not gonna take off. Okay, driverless car is a bad idea, stupid idea, and very dangerous idea. Very fucking stupid idea. Okay, so driverless car is not gonna take off. Okay, it's some stupid idea that's gonna last for a while, just like marijuanaism, gayism, and it will all disappear because it's a stupid idea. Okay, yeah. Okay. All right. So we have that. Okay. So I guess that's enough for the appetizer. And um so when we did the infinity algebra, we are talking about speed of infinity. Okay, speed of function, the eventual speed, right? The size of a function, eventual size, who wins is eventually relative size of that. Okay. Now, in this abstract algebra concept, um, we're going to talk about density of infinity. Okay. All right. So this slightly different discussion regarding infinity. Okay. So, but before we jump into that, we're gonna take a break. Okay. So, yeah, I did some vacuum. I cleaned my house. So it feels good. Tomorrow probably I'll do some laundry, my linen, to wash my linen. I do it on a weekly basis. man, it's kind of getting chilly here. So, um, so it's it's quite a bulky subject that we're gonna do because I that just couple of hours, I guess, uh, about three lectures. Th- I think about three lectures about abstract algebra that I watched. I think it's Monday. I think I learned a lot, and then I thought a lot. So there's a lot to talk about. Okay, so I'm like, I don't know where to begin. Let's continue this discussion of the general coordinate system, okay, where skewed coordinate system, okay, so it has to do with this linear combination of two vectors, is okay. Now we talked about we we are like everywhere, right? Because I was very much inspired by that abstract algebra lectures that I watched on YouTube. So yeah, I was everywhere because I was very much. I got a lot of ideas now. Okay, so we all level one by one. So yeah, if I eat animal, okay, animal become one with me. My if I chicken, that chicken, poor chicken, become my flesh, my hair, my eye, my brain, the protein. Okay, so poor chicken, right? Yeah, it become part of me. I eat that chicken. Okay. If a bear, I go to Alaska mountain this summer, maybe not, probably not because I don't do that anymore. Okay. I just run around my neighborhood. Okay, so or around my work. Oof, give me 1 second. It's just microwave. Yeah, everything's fine. I thought it was like popping. So yeah, if a bear eats me, hypothetically, I become part of that bear. All right, so it goes up both ways because in Alaska it happens. Yeah, people get eaten by bears sometimes. Okay, so bears in general they are not friendly animals. They are predators. All right, and we are very fat, weak, so we are very easy prey to bears. Okay, so yeah, so you have to carry guns and plenty of bear sprays, multiple bear sprays when you go deep in the Alaska mountain. Okay, because they are smart. They come out of nowhere. Okay, because they know how to stalk. They know how to hunt bears. Okay, so we are very easy prey unless we have bear spray and gun. One gun here, bear spray here. Okay, so yeah, use them both at the same time when bear comes charging at you. Okay. Yeah. All right, so yeah, it's like that. Okay, so me or chicken. Okay, yeah, add them together. You can add this stuff. Okay, so now my new vector will be something like that. Well, I guess that's not quite right. Okay, whatever. So let's say this is my chicken meal and I eat it. So now I become longer, bigger, stronger, I guess. Okay, I absorb it. I merge this chicken to me. Okay, but it's kind of status quo actually. Okay, because actually I as I live, consume more and more energy. Actually, I get shorter and shorter and shorter my energy level, right? So then I eat. So my vector, life vector, becomes shorter, 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 and I eat and I replenish the energy level by eating this chicken. Yeah, I get regain my strength. Okay, my energy level. All right. And we'll talk about this perhaps later because I just want to throw it out there. But what if I have okay? So what I'm trying to say is me and this opposite animal, okay, a rabbit, it doesn't quite change the world or produce something new. Okay, it's just me maintaining myself. So rabbit, very different animal, right? How about me and another guy? I mean, yeah, we can have a friendship, but we are both guys, so we cannot make any babies. So yeah, it doesn't quite work, right? But if there is me and a woman, she's kind of orthogonal. Why? Because she has both similarity to me and also dissimilarity to me. She and I, we are both Homo sapiens. Me, rabbit, we are just two different species. So we cannot have sex. Yeah, what do we do? I eat it, right? But me and a woman, she's Homo sapiens. But that's our similarity between me and that girl. We are both Homo sapiens. But so there's the similarity in species. I'm Homo sapiens, she's Homo sapiens. We are both human beings. There's similarity. Okay? Things in common. But there are also dissimilarity. Gender. She's a woman and I'm a man. She's female, I'm a male. So she got something in common with me and something very different from me. Okay? Then yeah, we can have sex and make babies. Okay? And there's this whole universe that opens up. Something like that, okay? Something like that. Me and another guy, we are both Homo sapiens and we are both males. We are too similar to each other. Me and a rabbit, I mean, me and a chicken, there it could be it is a male chicken. So, me and male chicken, yeah, we are same gender, rooster. But we are different in species. So what do I do? Yeah, I eat it. Okay. So this analogy isn't very perfect. I just wanna mention it to you. All right. Let's continue with this linear combination. Okay, you have vector A. Okay, and vector B. All right. If they are not 100, this theta, if theta is not 0 and it also is not 180, but any other angle between 0 and 180 or between 180 and 360, okay? If theta is angled like that, then you can express every single point in this two-dimensional space with some x times a. X is a scalar constant plus scalar variable. Y y times b. Okay, so x, y, they are variables and they are, and it says this is generalized coordinate x comma y in this generalized skewed coordinate system. Okay, yeah, these are the a and b. They are the basis vector of this coordinate system. Okay, they don't have to be one. The length doesn't have to be one. The angle between the two basis vectors doesn't have to be 90 degrees. is more generalized concept. Okay, any point in this two-dimensional flat space can be expressed in this coordinate system. Okay, because okay, a plus b. Okay, we do a parallelogram, right? Right here. This point, yeah, half of a plus b. Okay. How about point right? Yeah, this point what? 2 times b, comma 0. So this coordinate is in this skewed coordinate system. Okay. And also it's skewed and also stretched coordinate system. Why? Because the basis vector is no longer 1. It could be 2, 3, or it could be 0 0.5, 0 0.2. So yeah, it's kind of, it's first it's skewed coordinate system because theta is no longer 90 degrees, but now it's stretched or condensed coordinate system too. Why? Because basis vector is no longer 1. It could be more than 1, stretched, or less than 1, compressed. Okay, so it's but still it's on the flat two-dimensional surface, and also it's the axis, the straight line. Okay, because there's some other coordinate system where this axis is kind of curved, like on a sphere, on a hyperbola, three-dimensional hyperbola or parabola. Okay, there are other coordinate systems. I don't know too much about them. Okay, I just do flat surface. All right. Maybe one day later in the future, maybe. Okay, maybe. But my speculation is that probably I have better things to do than that. Okay, maybe politics. Okay, 'cause I want to get into politics as soon as possible. It's just that this humanology series, I've been doing this so that people watch this and I become famous and become the president. But it's not quite working. Okay, and it's a good thing in a way because if I'm not famous, I have more time to study and teach. As opposed to when I'm president, then I won't be doing this, right? If I'm very famous. So, and also if I'm not famous, I don't get into any trouble because nobody's watching this. Because I say things here that people would not like. So nobody's watching this, so yeah, I'm safe. I'm protected by this anonymity, this namelessness, anonymousness. Okay? Nobody's hearing what I say, so I don't get into trouble. So I'm being protected by anonymousness. Okay? So that's good. Alright, so this point is origin 0, 0 in this coordinate system. Here you have 0, b. I mean 0, 1. Here you have 0, 2. Why? Because it's 2 times of b right here. Okay? Here you have 0.5, 0, 0.5, 0, okay? And here you have, right here you have 1, 0, okay? Because it is a, right? A plus 0 times b, okay? So here you have 1, 1, okay? In this brand new coordinate system, okay? And in the original coordinate system, I mean, in the traditional rectangular Cartesian coordinate system, yeah, it is totally different, okay? So what's the conversion formula between the two? Well, it's a geometry problem. I guess we can talk about that briefly. Okay, so it's a yeah, sure. Well, first of all, stretched coordinate system. Okay, let's just think about one dimension. Okay, here's one, here is two, right? And let's say this is A, and this is I, right? So in original system, okay, we'll call it two. Original system we call it coordinate system zero. Okay. Now brand new system is one. Okay. Brand new system. So x0 was 2. Now x brand new system is 1. Okay, so how can we derive that? It's this. Okay, so in a stretched coordinate system or condensed system, yeah, you just divide the new basis, okay, by high, okay, by the original, okay. So that's 2, right? Okay, so x is equal to x0 times from 2 to 1 is 1 half. So yeah, yeah, it's that. Okay. Oh boy. Okay, 2 2, yeah, so that's the formula right here. All right. How about skewed system? Okay. I'm not gonna take picture of that. Oh, do I want to take picture of this? Nah. Yeah, sure. I don't really feel like taking pictures. I told you we are doing we are not even doing abstract algebra here. Okay, we're just because we got a lot of inspiration. So and that's good. That's good. Okay. All right. That's good. So we can erase this. Now with the skewed coordinate system, the conversion between old system and new system. Okay, so all right, and let's say it's 45 degree. Okay. One, one, okay, and according to the old system, the coordinate would be coordinate 0, right? According to the old system, this is yeah, it's geometry problem, right? This is 1, okay, 1. Um, 1, 1 over square root of 2, 1 over square root of 2, so it will be which is about this is our square root of 2 over 2 is equal to this is like 1.4 something like that, right? over 2 is like about uh, point 0.7, 0.7, okay? So then it will be like y coordinate will be like zero point 0.7, right? S coordinate would be 1 plus 0 0.7, so 1.7, something like that, okay? So basically, you have some uh, to generalize, okay? To generalize, you have x0 here. Ah, boy. Let's say here you have x0 comma y0, all right? And in this original rectangular traditional Cartesian coordinate system. Okay, now you have brand new coordinate x comma y. Okay, so meaning from here to here it is x. Okay, and here to here that's y. All right, and now it's general angle theta. Okay, all right, you following me? Then x0 is equal to x plus y cosine theta. Okay, y0 is equal to is the coordinate in the traditional Cartesian system. Okay, y0 is equal to yeah, y times sine theta. Okay, that's that. All right. Okay, and then in a stretched coordinate system, it was like what you had what this you have brand new x. There was x0, right? No, no, no. You have 2 as a brand new system is supposed to be just 1, and x0 is supposed to be 2, right? So here you have what x0 is equal to x times um, you have to multiply by 2. Okay, so uh, the I absolute value divided by I guess I0, all right, absolute value which is 1. Brand new I, that's the basis vector for this stretched coordinate system or condensed coordinate system. Okay, so um, yeah, so 1 becomes 2. Okay, because it's stretched coordinate system. All right, so you combine these two guys, okay? Then you will get the final um, conversion formula for the stretched and skewed coordinate system. Okay, so we probably just leave it as an exercise and homework because we don't quite feel like doing this because we got a lot to do in this abstract algebra. Okay, so we don't want to waste energy on other stuff like this. Okay, this is more tensor stuff. We're not doing tensor here. Okay. All right. So, by the way, I'm running out of vodka. So what do? I just drink wine and stuff. I'm kind of wondering how can we combine those two? Well, let's just think about this guy, okay? Because here up here you have both x and y. Here you only have y, so it's a lot easier. All right, all right. Okay, so we rotated it. I mean, we kind of skewed this y coordinate by 45-degree angle, so we got that. Now we are changing again by stretching it. So the final product would look like, let's say, well, you have y is equal to y0. So let's say this is y1, okay? After rotating, skewing this coordinate, okay? So y1 is equal to y0 over sine theta. Okay? And if we stretch it now, it will become something like this. y2, here you have x1, okay? y2 is equal to, I'm making sure you can read this, alright? So y2 is equal to y1 absolute value of j it goes downstairs, all right? Upstairs, absolute value of j0. Better say j1. Oh. Okay, because here you have 1. Okay, so yeah, we are just commutating, okay, permutating, okay, substituting, okay, Instead of x, we using y. Instead of 0 and 1, we are using 1 and 2. Okay? So, okay? So this becomes y2 is equal to y0, but between 0 and 1 and 1 and 2, yeah, the length isn't quite length of this. When we first rotated, skewed this coordinate system, we didn't do anything with the length. Okay, so uh, yeah, we better keep this as a 0, y0, and j2, because j0 and j1 absolute value, they are the same, because we didn't make any change. We didn't stretch or compress in the first round. The first round we just did the rotation, the skewing. Okay, so there we go. We have it. We have it for y. Okay, I'm so sorry that it's running out of space and whatnot, but well, you can read it. So okay. Maybe it's time that I buy the third whiteboard. Maybe. Okay, so I might. So what do I need to buy next time I go to Walmart? Let me write it down. Okay, I buy a whiteboard and trash bags. Maybe I go back to Walmart tomorrow. Okay, so I trash bags, whiteboard. There was one more thing I need to buy. Hmm. What's that thing yeah, vodka. I need to buy vodka. Okay. Yeah, I went to Walmart. I think it was yesterday. I bought some kale, and oh man, it made a whole difference. Kale is so good. I also like collard. Okay, probably next time I will buy collard. Yeah, I put some kale in my food, and oh, they're delicious and they are very nutritious. And also, yeah, nowadays, during the lunch, I run to Chinese restaurant, right, and then I to that this time and today earlier during my lunchtime, I bought this lunch menu with some vegetables in there, and it was very good with yeah, onions and celeries there. Yeah, this particular Chinese restaurant joint, they know how to cook just right the vegetables. It's not mushy, it's not too tough, it's just right in the middle. Yeah, they know how to cook vegetables. So yeah, I like this Chinese restaurant a lot. Okay, so it's a franchise, national American franchise. I'm not gonna tell you the names because I could become a very notorious figure. So I don't want their business to be hurt by association with me because I could be a very notorious figure. I don't want to hurt their business. Okay, so right, so But if I have to be positively, famous person, then yeah, I will endorse them. I can even show up in their advertisement and get some money. Okay, because I won't be lying. Yeah, I really like that national franchise Chinese restaurant. If I gain like positive fame, yeah, I may appear in their advertisement and endorse them because I really like that restaurant. Okay, I also like McDonald's and Burger King. Would I and Subway sandwiches? Would I appear in their advertisement? Yes, because I'm genuinely a huge fan of them. Okay, I used to work for them too, as a drive-through crew, and sandwich maker. Yeah, I would love to. So why am I free to talk about McDonald's and Subway sandwich and Burger King when I'm not talking about this Chinese restaurant? It's because this Chinese restaurant is not as big as McDonald's or Burger King. Even if I gain notoriety, it's not gonna hurt McDonald's. People will not hate McDonald's just because they hate me and I love McDonald's. It's minus times plus, okay? Because McDonald's is very big, and this Chinese restaurant joint is not nearly as big as McDonald's or Burger King or Subway. Okay, it is national joint, but it's not that big. Okay, so yeah, yeah. Hey, even if I love McDonald's and people hate me, that's not gonna hurt McDonald's because McDonald's is really big. Okay, so all right, okay. So let's finish this up because now that we started it, and because it's very very simple from here. Okay, um, it's real easy. It's something we started, so let's finish it up so that we can move on and forget about it. Okay, so otherwise, I kind of regret not having finished that. Okay, so x is equal to x0 minus y1. Actually, sure, cosine theta. Okay, that's we first rotate and then we stretch. Okay, so is equal to x0 minus what is y1? I guess I erased too much, right? Y0 sine theta. Okay, so y0 sine theta. That's no, that's not true. So y1 is equal to cosine theta. Y1 is equal to y0 over sine theta. Okay. Y1 is equal to y0 over sine theta. So cosine theta over sine theta. That's cotangent theta. Okay. All right. It's just 1 over tangent theta. Okay. So yeah. Okay. Yeah, I'm kind of going fast because we want to get over this shit. Okay, so yeah, just catch up. It's not that difficult thing. Okay. Now we're stretching this shit. Okay, so when we stretch this x coordinate, um, x0 is equal to x1 because when we rotated it, the length didn't quite change. Okay, so but actually it did. Well, it doesn't matter. So the basically the concept is here is when you stretch it, okay, or compress it, okay, so now x2 is equal to x1 multiplied by I0 I1. Okay, so x1 what is x1? X1 is this guy. Okay, x0 minus y0 cosine cotangent theta. Okay, and then you multiply by I0 over actually this happens to I2. Okay, because I0 is equal to I1. Okay, because yeah, we didn't change the basis. All right, when we rotated it. Okay, so okay. I mean, in terms of absolute value, yeah, we did change the basis vector in terms of angle, but in terms of this absolute value, yeah, we didn't change it in the first round because first round we rotated. Okay, second round we compress or stretch. Okay, so yeah, we have formula here. Okay, I'm sorry it's not that pretty. Okay, but at least you can read this, right? You have this guy here. Okay, y2 expressed with y0 and j2, x2 expressed in terms of x0 y0 theta and I0 and I2. Okay, so that's the complete formula right there, and we're gonna take a picture of this. Okay, and then then we'll take a break. Okay. All right, let's take a break. Oh boy. Sorry. We'll take a break, okay? All right. Okay, we are back, and all this conversion between two coordinates is I may have made some minor errors. It doesn't matter, okay? It's very mechanical process. If I made some error, I'm sorry, okay? But because this is not very important in our discussion at hand, okay? Because we are doing abstract algebra here, okay? We are not doing any tensor stuff, okay? So yeah, it's very. Let's just take a break from abstract algebra, alright? So that's all it is. It's not that important. So that's why if I made my error, then correct it, okay? So it's not that important for now, right? So okay, so let's get back to this abstract algebra stuff, alright? So you have these two vectors, this whose angle between is neither 180 or 0, okay? So yeah, you can express, because you can shorten this base vector, or you can elongate this vector basis vector, okay? And you can shorten this the other basis vector, or elongate basis vector, and then yeah, all this, you know, you can express any point in two-dimensional space, okay? All this, every single point in two-dimensional space. Or you go to the other direction, okay, the other direction, right? Then yeah, you have this, you know, okay, all these points in two-dimensional space, okay, and you flip one of them, like this guy, and you don't flip the horizontal guy, then yeah, it's like a minus b, okay? You have minus b plus a, okay? All these points are expressible. All these points by this parallelogram, this vector summation, okay? So x times a plus y times b, and this is our brand new coordinate x comma y, okay? So it's a variable x and y, okay? A and b, they are constant basis, okay? They don't have to be equal length, they don't have to be one, they don't have to have this 90-degree angle between them, okay? Or here, uh, you have a minus a plus b, okay? Minus a plus b, minus a plus b, and all the stuff in between, okay? Okay. Yeah. Like occupying Wall Street, whatever. Okay, so it doesn't matter what angle between these two basis vector and their length, as long as their length is neither zero nor infinity or negative infinity. And their angle between the basis vector is not zero, not 180, and their length is neither zero nor infinity, then yeah, you can express any point in this two-dimensional space in terms of this two basis vector a and b. Okay? So that's the linear combination concept. All right? All right. Yeah, I'm really running out of this vodka. Okay, so it scares me a little. Am I workaholic and alcoholic? Nah. To me, alcohol and this work is about pleasure. Alcohol is a fuel for this pleasure, so it's no big deal. Okay, so yeah, whatever. Okay, all right. Let's switch out the drinks. Yeah, I could have stopped by liquor store on the way back home from work, but I didn't. Okay, because man, I plan to vacuum my house and sweep the that doorway and take the trash out because today's Thursday and man, that's too much work. Okay, so should I go to liquor store and buy stuff? No, give me a break. That's too much work too. Okay, so I didn't go to liquor store on the way home, right? Okay, so let's formalize this. All right, let's be mathematically rigorous. Okay, regarding this extension, linear. You have two vectors, right? Vector A, two basis vector. Vector B, okay? Now, x times A, this scalar, it can be plus 1, minus 1, 0, all right? Plus y times B vector, okay? A and B are non-zero vectors. And the angle between the two, they are not 0, they are not pi. Okay, somewhere between, it's not 0, it could be 90 degrees, but it doesn't have to be. It's some angle that is not 0 nor neither 0 nor 180, okay? And also, that's first criterion. They are not along the same line. They are not opposite to each other, and they are not same direction, but they're kind of angled in between, okay? Including the 90 degree, okay? And also, second criterion, the length of vector A or vector B is neither 0 nor infinity, okay? If that's true, two conditions. All right, let's write it out. It's something brand new, okay? This is like vector A comma vector B. Their uh, lengths is not equal to zero comma infinity, okay? This is shorthand of saying absolute value of z is not equal to 0 and absolute value of 0 is not equal to infinity. Yes, okay? And absolute value of b is not equal to 0 and absolute value is not equal to infinity. Okay, it's a shortcut for that. So this is criteria number 1, okay? And criteria number 2, so it's like logical and, right? We are doing Boolean algebra here, okay? The angle between vector A and vector B, okay, is not equal to 0 and it's not equal to pi, okay? Or we can say n pi. It's not 2 pi, it's not pi, it's not 3 pi, okay? Yeah, n pi, okay? and it's all logical and operation. If that's all true, and then yeah, if that's all true, then x times a vector plus y times b vector is equal to r squared, meaning two-dimensional coordinate. Okay, it's nice introduction and nice bridge, like bridge code in cinematography, to discuss the next topic, r squared. It's a Cartesian product. Okay, so now let's talk about that. All right. We're gonna take a picture of this because it's kind of neat. All right. We'll take a picture of this. Okay. Give me 1 second. So, let's see. R squared. It's just talking to my friends, okay? R squared is like it's a Cartesian product. Okay, it's a very interesting concept. Okay, so in set theory, okay, there's a set is an unordered set. Okay, like okay, so in set theory, when you first learn it, they teach you like yeah, it's unordered. Ordering doesn't matter. You know, 1, 2 is equal to 2, 1. Okay, so that's unordered set. All right, and then there is ordered set, like you know x comma y, x comma y. So 1, 2 is not equal to 2, 1 because this is an ordered set with regular parentheses as opposed to curly parentheses, curly bracket. Okay. All right. But yeah, unordered set where ordering does not matter. Here you have ordered set where ordering matters. Okay. I think it's time to take a break, okay? Because I don't want this momentary hiccup become permanent. Okay, so let me take a breath and we get back to this. Okay, so all right, take a break. Okay, my house is now being warmed up. It feels very nice. Let's take a break, okay? Let's take a break from all this mathematical mumbo jumbo. Yeah, so I have this contingency alcohol, wine and beer. It's not as good as vodka, but because vodka happened to be my favorite. It's so clear, like water, kind of watery, but also very strong. Vodka, it has no color. Whiskey is kind of like brownish. It's strong. Vodka is very strong liquor, and also it's clear, so I can put stuff in there like this horseshoe mushroom. Okay, but yeah, I'm running out of vodka. Totally ran out, but I have wine and beer, so emergency, contingency, alcoholic drinks. So not as good, but it will do for for tonight. Okay. All right. So yeah, that was the short brief break. Small talk. Okay. So let's talk about Cartesian product. Cartesian product is like this. Okay. You set A is what 1,2 is a set, unordered set. Okay, unordered set is by default. When you talk about just set, it means unordered set. Ordering does not matter. Okay, it's just like plus sign is implied. It's by default. So one means plus one. Okay, so 1,2. Okay, set B 3,4. Okay, Cartesian product is a new set is equal to uh, it's called tuple, like two tuple. You can generalize n tuple. Three tuple is three-dimensional coordinate system. Okay, so x comma y comma z. A tuple, again by default, a tuple means two tuple, like it's x comma y. Okay, it's what 1,3, comma 1,4, comma 2,3, comma 2,4. Okay, that's the Cartesian product of these two sets. Okay, it's the exhaustive list, exhaustive enumeration. That's what Cartesian product is about. Yeah, you can do A times B times C, then you have this three-dimensional with 9 elements. If C is what 5,6, okay, and I'm not gonna write it out of that to you. Okay, so okay, is this 9? No, I don't think it's 9. It's like 2 times 2 times 2 is 8. Okay. For the heck of it, sure. 5,6. 135, 136, okay? 145, 146, okay? 235, 236, 245, 246. How many is that? One, two, okay, it's three diagram, okay, combinatorics. 3, 4, 3, 4, and 5, 6, 5, 6, 5, 6, 5, 6, okay, so 2 times 2, what, 2 times 2 times 2 is equal to 8. 1, 2, 3, 4, 5, 6, 7, 8, okay, so yeah. That's that. Is third order Cartesian product. A times B times C. Okay? And notice the similarity of this Cartesian product and polynomial product. Okay, you have what, x1 plus x plus y multiplied by a plus b. Okay, what have you, ax plus bx plus ay plus by. Okay, okay, what if you have m plus n multiplied by this? So you have this guy multiplied by n plus n. My goodness, I'll just say it. Okay, axm plus bxm plus aym plus bym plus axn plus bxn plus ayn plus byn. So there are 8 of them. Okay, so the expansion of this polynomial is the same as expansion of this Cartesian product. Okay. Why are we talking about this? Because of this. All right, so we'll get there. Okay, we're just doing step by step. All right, so square root 2 and square root of 3, it does not quite mix. Okay, yeah, you can merge this one times square root 2 plus what, 2 times square root of 2 is equal to 3 times of square root of 2, right? They can merge. But square root 2 and what is like what? Square root 2 is like 1.414 blah 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 blah, right? Square root of 3 is equal to what? 1.732 blah blah blah, right? So they're irrational number. You cannot express these radicals, okay, in terms of a fraction. Okay, what is a fraction? Some integer over another integer. Integer divided by another integer. So you cannot express that because this square root or cubic root, these radicals, they don't come from division. They come from this power operation, which is one level higher than multiplication. So it's a higher number systems. That's why you cannot express this with these lower guys like multiplication and division. Okay, so okay. So yeah, square root 2 of and square root of 3, they are totally different species. They don't mix with each other. You cannot merge 2 of them by addition. Then how can you merge? Multiplication. Why? Because multiplication is one order higher than addition or subtraction. Also, you can merge this square root of 2 and square root of 3 by division. Okay, let's do it. You know, it's all about ordering of this operator. Okay, square root of 2 plus square root of 3, it just stay there. You cannot merge them to one single term. But square root of 2 multiplied by, which is what? Square root of 2 plus square root of 3 is too light, right? Okay. I use a dark green. It just stay there. You cannot merge those two into one single term. But square root of 2, what's the next order? Yeah. Because plus addition, ordering, It's ordering of this operator. Okay, so if you have paid attention, if you remember this general operator concept, yeah, a plus a plus a plus a n times, it's like n multiplied by a, right? So the second order, a times a times a times a, blah blah blah. You do that n times a to the nth power operation. So plus operation, multiplication, power operation is like first order plus, second order plus, and third order plus, and you can continue on and on. Okay, so that's the generalized operation concept. Okay, so this is equal to a square root of 2 multiplied by, we don't do this x because it looks like character x. Okay, so we do this star, just like in computer programming convention. Okay, yeah, yeah, it get merged into one term. Okay, how about uh, square root of 2 and minus second plus of 3. This is what? Square root of 2 divided by square root of 3 is equal to square root of 2 divided by square root of 3 is equal to 3 square root of 6 over 3. Okay, so it's kind of merged into not 1 but 2, but it's still merged. Okay, uh, but not exactly because you have two terms here. They cannot quite merge into one. You still have two numbers. They don't quite merge like here. Okay? So sometimes it absorb and merge, sometimes it doesn't. Yeah, kinda, but not exactly. It's just like square root of 2 plus square root of 3, it doesn't quite get merged. Okay, so it's kind of similar to that. Okay, but close enough. Because, yeah, I studied abstract algebra. I tried to learn it in the past, and then I went to YouTube last Monday, okay, 3 days ago, and there was this fantastic Australian mathematics professor who studied in Canada and in America, uh, in Yale University, in Canada, maybe Ontario or Vancouver. I'm not sure. Okay, but he's very good professor in mathematics. In I learned from him in YouTube videos. It was nice and kind and generous to put his lecture in the YouTube video. So I learned some abstract algebra. Yeah, it's so cool. I was inspired, but I was not satisfied with the way abstract algebraists have done. So I want to improve upon what they have done. That's what we are doing here. Okay, because I was not satisfied with this traditional abstract algebra, which has very short history, like 100 years or 200 years. Okay, so I want to contribute to that because what they have done is good, but there's still room to improve, and that's what we are doing here to fill the gap, to make it better, at least in a pedagogical, instructive, educational way. Okay, at least. Okay, so all right. Oh boy. Okay. Ah, it's time to take a break. Let's take a break. Okay. So this is heavy stuff, and I have full-time job. I just came back for get back home from work and I did vacuum my flowers and sweep the floors and let's take it nice and easy. Okay, I'm cooking my dinner and yeah, let's take a break. Okay. Okay, here's my contingency drinks, my wines. We'll be back. Okay, we are back. We have like 1 hour or so left, so probably we'll have take one more break between before we end this episode. Oh, this wine is good because it's been sitting out here like room temperature without any cap, so it acidified. Oh, so good. Yeah, they're good. Ooh, so good. Okay. So yeah, square root of 2, let's say x times square root of 2 plus y times square root of 3. Okay? So these two radicals, square radicals, it act like this vector, two different vectors, each of which is not does not quite have same direction or opposite direction, but they're kind of like halfway in between. Okay, so I mean, we don't have to go to this complex, like what real and imaginary complex system, two-dimensional complex system. We don't have to do that. Okay, so but it kind of looks that way. Okay, so yeah, it looked just like x times vector A plus y times vector V. Okay, when these two guys, they don't quite mix. It's a this two different bases in this two-dimensional space. Okay, it kind of behave like that. Okay, so that's the analogy, similarity there. Okay, we are doing step by step, very slowly, because abstract algebra, the way they did it, I mean, it's cool, okay, but we want to improve upon what they did. The field theory, group theory, ring theory, it's so cool. Okay, they made a lot of good discoveries there. Yeah, I can see that, yeah, Galois theory, Abel theory, whatever. Okay, so we appreciate that. We just want to improve upon what they have done. We want to be better. Okay, perhaps more thorough, more complete, more perfect. Okay, that's all we are doing here. Okay, so all right. Love this wine. Dark chip wine being sitting out there in the room temperature without a cap, and all this bacteria and virus came in and they acidified it for me. Good bacteria, good fungus, good virus, whatever. Very good. Okay. Now I gotta pour more wine, but yeah, I'll do that later. Okay, so we gotta move on. All right. Okay. But before we introduce these two radicals, like square root of 2 or square root of 3, let's just deal with one radical, okay? So, because it's all the same, all right? So, it's just like a plus bi, okay? This imaginary number, what is I? I is equal to square root of minus 1, okay? So, a part is the real number, like re, okay? B part is this imaginary constant for this I, okay? You have in complex number system, you have what? Real number axis and imaginary number axis, right? I learned this in Korean high school. So yeah, you have this what the circle and you have this, you know, this what pentagon, right? And they are the roots of what x to the fifth is equal to 1. Yeah, I learned this in Korean high school, and I also learned this again in this briefly in this abstract algebra lecture series by this Australian Yale educated, and I think it's Ontario, not Vancouver. I think so. It was Ontario. Yeah, he was in Canada, United States. Okay, top schools, maybe University of Ontario or something. I don't know. But he's now in Australia, and yeah, it was nice to revisit. Okay, yeah, you have what this you know symmetrical, beautiful geometry of this pentagon, complex complex coordinate system. I get it. Okay, we get it. All right, but we are not gonna go there because maybe it's sometime later. All right, it's just real number and imaginary number. They don't mix. They don't merge. Just like square root of 2 and square root of 3. They don't merge in terms of this addition. I mean, if you multiply a times b I, it becomes, yeah, they can kind of merge a b I, right? They kind of merge, but in terms of addition, and this is what ab is what 2 times 3, yeah, 6, right? C times I, yeah, you can merge in terms of this multiplication, but in terms of addition, yeah, not quite merge. Okay, all right. Addition or subtraction and multiplication and division. Okay, a times or divide by. Okay, all right. Yeah. So sometimes they merge, sometimes they don't quite merge. They are separate. It's like segregation, like racism or this gentrificationism or gentrism, all this class hierarchy, they don't quite mix, they don't quite merge. Okay, if they are two different classes, if they belong to same class, yeah, they are more, they merge, they mix, right? So there's a humanological analogy there. Okay, so boy, yeah, okay, so 2 plus 3 times of square root of 2. Okay, it's like 2 plus 3i. They don't quite merge. Or it's like 2 plus 3x, or 2x plus 3x squared, or 2 plus 3i. Yeah, they don't quite merge together in terms of this plus operation. If you multiply, yeah, they can merge. This becomes what? 6 square root of 2, 6 times x, 6 times x cubic, 6 times I. If you multiply, yeah, then they can merge. But in terms of this plus operation, they don't quite merge. They just stay separate. Okay, like Republican Party and Democratic Party. Okay, they don't quite merge to one party. Okay, all right. Let's take a break from all this mathematics. Okay. Yeah, I mean, they say, oh, America is melting pot. I don't like that. Okay, I want America to preserve and protect their diversity, ethnic groups. Like you have Korean Americans, Japanese Americans, Chinese Americans. I want them to be culturally separate so that we don't just mix them all together, melt them, and no. I mean, yeah, soup is great, but you don't want to overheat your soup to this gruel. This no. We want you rather cooked a soup, vegetable soup, whatever soup, just the right, not overcooking, not undercooking, just kind of in the middle, so that vegetables still have these vegetables Meat still have meat, rice still have rice. You don't want to overcook this chicken noodle soup. Then everything will be just mixed together. It's like mushy and you don't want that shit. You want to have meat, rice, and vegetable. Okay. You don't. Yeah, in your stomach. Yeah, you have this stomach acid, and they get all mixed together. They get mushy, but when you eat, you want them separate. Okay, so you don't want to overcook and get it all mushy and all melting pot. No bullshit. I don't like this concept of melting pot. No, we want America to be like this: blacks, whites, Asians, Arabs, Hispanics. Okay, if they all intermarry, interracial sex, interracial marriage, then we will all look like Hispanics. Okay, we don't want that. We want blacks to be blacks, whites to be whites, Hispanics to be Hispanics, Arabs to be Arabs, and Asians to be Asians. We want diversity. We don't want to mix them all together, this melting pot. No, that's a bad idea. Okay? All right. So it's like this, okay? Yeah, we don't need two radicals. We just need one radical because, and we are not talking about rational number or real number. We just talk about integers because the rest is the same. Okay, so one plus two plus three square root of two. Okay. Let's take a break, okay? Because I gotta get more wine and water. Let's take a break. Okay. We'll be back. Okay. All right. All right. We'll be back. Okay, we are back. Yeah, just washed my face. Always refreshes me, and little things in life. Okay, so boy, we have 1 hour, 15 minutes left, and slightly less than 1 hour. That's enough. Um, okay, so 2 plus 3 times square root of 2. Okay, so we are being very mathematically rigorous, and uh, we probably have to come up with new terminology, expansion, as opposed to group, ring, field. Nah, because so I watched this lecture series, about three of them, by this Australian professor, mathematics professor, and he's very intuitive kind of guy, as opposed to formalistic. I really liked his lecture, and he emphasized on this mathematical history, these mathematicians, what year, all that stuff. I really like that. Okay, so yeah, Poincaré also was kind of anti-Bourbaki, because Poincaré was more like intuitive kind of guy. Okay, so and they're like creative kind, kind of like laid back, kind of like Rene Descartes. He's kind of lazy ass. He would just lie down on his bed, or I want to lie down on my bed, and he was looking at his ceiling in his bedroom, and there was this fly. A story says, yeah, that's how he came up with this Cartesian coordinate system. That's the story, but we don't know whether it's true or not. But yeah, these creative individuals, they tend to be lazy, laid back, leisure, and I am that kind of guy. Okay, I don't want to work too much. Okay, I don't want to learn and learn, study. No, I want to study somewhat, but I'm a kind of bullshit or shenanigan. So yeah, there's it's creative kind, intuitive kind, and yin and yang. The opposite of that is formalists. Okay, they are like they always wake up at like 5 o'clock in the morning, like a clock, and then they do what? Okay, formalistic kind of people, regular. They are good learners, good teachers. They go to Ivy League schools, but we creative individuals, we don't have the best GPAs. We don't go to these top schools. We are kind of like outliers, kind of like lazy, but we are creative. Okay, so there are two kinds of people. We need both of them. Okay, yin and yang. Okay, this formalists, they are very good at proving stuff. Okay, we creatives, creationists, creative people, intuitive people, we are more like inventors. We are very good at come up with brand new ideas. Okay, we are not good at learning. We don't have high GPA. We don't go to top schools, but if we go to top schools, we tend to drop out. But we tend to be very creative, intuitive kind of people. Kind of lazy, but we need both kinds of people. Okay, elitists and what? Communists? No. Intuitivists. How about that? Intuitivism. Yeah, more creative. Create creation creativists. More creative kind, okay? Yin and yang of the universe. Alright, so alright. Yeah, so we intuitivists, we are good at looking at this general pattern, the forest. Formalists, they are very good at looking at individual trees. We need both kinds of people, okay? Like mechanical people who are good at proving stuff, like mathematically rigorous, and creative people, yeah, mathematically relaxed, laid back, lazy, but intuitive. We need both kinds. Okay, it's like yin and yang, men and women, king and servant, employer, employee. Okay, it's yin and yang, it's a balance. Okay, it's dualistic structure of the universe. Okay, we need them both. Okay, sun and moon, night and day, whatever. Okay, black and white, whatever. Okay, all right. So, um, before we get into this 2 plus square 3 times square root of 2, let's focus on 3 times square root of 2. Okay, we are being very very mathematically rigorous. Okay, so going back to the basics recursively. Okay, is this: you have this set of integers. Okay, yeah, it's a set, it's not a tuple, so it's not ordered set. We're using curly bracket, but you know, ordering kind of matters. Okay, ordering kind of matters. Okay, kinda. All right, so that set of integers. Okay, we call it I for integer. Okay, and what if you multiply this thing? I almost said motherfucker. Okay, I'm sorry. No offense to mothers, because mothering, they're the one single most important job in the world. Mothering, okay, because they are giving birth to and raising the next humanity, next generation. So mothers, yeah, the single mothering is a single most important job in the world. Okay, it's about future generation. Okay, so and there are people who never get retired, old people who still works, or they are my heroes. Okay, my role models, people in their 80s and 70s, they still work. People who never retire, they are my role models and my heroes. Okay, so right, all right. So let's multiply this set by square root of 2. Okay, so square root of 2 multiplied by this infinite set. You know, let's not even talk about infinite set. Finite set. We call it A. Capital A, okay? Because just like this Australian professor said, yeah, do you wanna do some fancy stuff? Just stop, okay? Do some finite stuff first before you get into this fancy infinity stuff. Go back to the basics, okay? Yeah, let's do that. Is equal to what? Minus square root of 2, comma 0, comma positive square root of 2, okay? So it's distributive, all right? We are defining a brand new operation between a single number and a set. And this single number can be thought as a set with one element. Okay, so it's kind of like Cartesian product. Okay, we'll see that later. Okay, single number can be thought as a set with one element. Okay, we'll see why this makes sense later. Okay, because I thought about it and it does make sense. Okay, so I'll share it with you later. Okay, that comes later. Okay, all right. So we have that. Oh boy. You know, we don't have to even think about integer like negative number. We only need to think about positive integers. Not even zero, okay? Just one and two. Alright. Positive, even not natural numbers, just one and two. Alright? So, one and two, okay? Set of two natural numbers. You multiply by square root of two, okay? We are defining a brand new operator between a number and a set is equal to what? Square root of 2, comma, 2 square root of 2. It's just distributive, okay? Brand new definition, alright? But we can also think about square root of 2 being a set of one element, okay? Why does this make sense? Will come later, okay? So, alright? But for now, just take my word for it, okay? Alright. Now, we're gonna try something brand new, alright? We're gonna think about addition. 1 plus is a number, 2 comma 3. We are gonna define addition between one number and a set. Yeah, it's just distributive. It's like what? 3 comma 4, right? Yeah, it's distributive as if this plus is like multiplication, okay? And you have to notice this. It's like 1 plus parenthesis 2 set 2 singleton, okay? And set 3 singleton. A set of one number, okay? And also this one is a set of one number. So a number is actually a set of one element. That's a brand new way to look at it, okay? So I looked, I did some Google search, Wikipedia, web surfing, and there's this what's called category theory. And they're visionaries, pioneers, frontiers who want to reformulate this fundamental mathematics in terms of graph theory and arrows and objects. I admire, I respect that kind of ambition. All right, so, and that's kind of what we're doing here. Okay, we want to. So category theorists, they try to redefine, they try to found the existing mathematics, not in terms of set theory, which is very dominant, mainstream, but in terms of category theory. Okay, they try to replace this zeitgeist, this time spirit, or this paradigm. They try to make a paradigm shift. Category theorist. I appreciate that. Okay, but they were not successful. Okay, but I learned that spirit, that ambition from category theorists. Okay, just like this Morpheus in Matrix movie said, perhaps we can succeed when they couldn't. Okay, yeah, well. So we are defining a number, redefining a number. We are giving, providing, proffering this brand new perspective. Number maybe it's a set of a single element of itself. Okay, so and what is distributive? Okay, it's like one plus set two union set three. Okay, so plus here is like multiplication, and union here is kind of low guy, like plus multiplication and plus. Okay, so it's one. It's like one times two plus three. Okay, so, and it distributes. Okay, because union is kind of lower guy. It's like set theory, you know. Plus algebra. It's like multiplication. It's a higher dimension operator. Union kind of low, like addition, you know, elementary stuff. So okay, because what I noticed in his this Australian mathematician professor's lecture is that, you know, there's this Friedrich Gauss and Abel Galois and Cauchy and Lagrange, and also there's Pythagoras and Plato, Socrates. Okay, these people with very in the back in the age, if they survive, they get more credits. The older they are, the more credit they get because they survived after all these thousands of years. Okay, so this modern thing, like 100 years ago, 200 years ago, it does not carry as much, nearly as much weight and authoritarian weight, authority, credit as people who lived like 1,000 years ago, like Plato, what Diophantus or Pythagoras or Euclid, Aristotle, or yeah, people who like Gauss, what 200 years ago. Yeah, it's kind of new, okay, but like Pythagoras, like 2,000 years ago, okay, he carries more weight, okay, because he's older, more ancient. Gauss, yeah, kind of new guy, you know, so okay, so yeah, all the stuff like audition, it carries more weight than this set theory, the scale contour. Yeah, it's like what 100 years old. Audition, thousands of years old. Okay, so it carries more weight. It have more seniority. Okay, so it's a higher dimension. Okay, so that's why it can distribute, just like multiplication, higher order operator, then plus. Okay, it distributes. Okay, so this guy is like okay, that's what it is. So yeah, one plus 2,3 is 3,4. Okay, it's long-winded this way of saying this very simple thing. Okay, why is this worthwhile to explain? We'll come back to it later. Okay, so we have only 30 minutes left, and okay, and we'll take a picture. I'll take a picture of this. Okay, then I'll zoom it in for you so that you can see clearly. It's very simple concept. It's nothing difficult. Okay, and but it is something very important. Okay, because I'll tell you later. Okay. Okay, we'll take a picture of this and we'll take a break. Okay, I'll zoom it in for you and then we'll get back. Okay. All right. Yeah. Okay, that's good enough. All right. Yeah, I continue to cook my dinner and all that. Okay, we are back. Um, so we are calling for a brand new nomenclature. Nomenclature, brand new. Yeah, it kind of neologism. Neologism, okay. But we have to because field theory, group theory, ring theory. I don't quite like the way they named it. Yeah, hey, I'm an English second English speaker. My native language is Korean. Okay, so, but all these mathematicians, geeks and nerds, gooks, whatever, feminist, Amy Nether. I don't know if she's feminist or not. Whatever. Okay, I'm just joking. Okay, so they field theory, group theory. No, I don't think this is the right word for it. I think the better word for it is expansion. You are expanding, okay? So yeah, field, yeah, I got it. Rice field, cornfield, wheat field is field. Like two vectors, they're adding together, x times vector A, y times vector B. It can express all these points in two-dimensional coordinate system. I get it, okay, but better term is expansion. So we call this expansion theory because they didn't pick the right word for it. Okay, because they are geeks, nerds in mathematics, so they're not good at English. They don't have good conceptual this vocabulary. We are better at it. Okay, because I know many languages. I have accent, heavy Konglish, Korean English accent. Okay, but I know about languages, not just English and Korean, but French, Italian, Russian, Arabic, some Hebrew, not much. But all I know about Hebrew is Shalom and Aleph. Okay. But yeah, we are. I'm a humanologist. Okay, we are the best of the best humanologists. Okay, we know everything, little bit. My abstract algebra knowledge is very shallow, but I know other stuff. Okay, I know about movies, singing, dancing, martial arts, politics, religion. Okay, so we have lag over them. We have this advantage, this leverage over them. Okay, so field theory, no, it's better be called expansion theory. Okay, so expansion algebra. We are expanding things. Okay, all right. I believe I took a picture of that. Let me make sure if I did. Okay. Okay. Yeah, during the break, I took some picture of the sky, Alaskan spring night sky. Yeah, I took picture of this guy. Okay, so I took picture of this whiteboard. So yeah, I can erase this. Shit, almost I said that. Now I said it. Okay. Okay. So it's like this. Okay. So you have x plus y times square root 2. Okay. It's like 1 plus 1 times square root of 2, or 2 plus 1 time. Let's be well ordered. Okay, 1 plus 2 times square root of 2. Okay, 2 times, 2 plus 1 times square root of 2, and 2 plus 2 times of square root of 2. Okay, it's like exhaustive enumeration, just like in Cartesian product that we talked about like an hour ago. Okay, see where I'm getting at. Okay, so it's a set union. All right, when x is equal to, it's a variable, right? It's a set. Here, set of 1 and 2. Okay, y is a variable. It changes, it varies. For now, it's a set of just 2 elements. Okay, union, this is one number. Okay, just one singleton, set of one number. Okay, union. Okay, and we're gonna shorten this, abbreviate it as 1 comma 2 set of 2 elements plus square root of 2 times 1 comma 2. Okay, you got it. That's what I've been trying to tell you. We are running out of space, which is equal to 1 comma 2 plus square root of 2 comma 2 square root of 2. Okay, I told you we are running out of space. I'll zoom it in for you. Okay, so it's like 1 union 2 and square root of 2 union 2 square root of 2. Okay, so and union, that's kind of low guy. Okay, it's like comma is this union. Okay, comma union plus higher thing, this ancient algebraic thing, comma union set theory. Yeah, you're kind of low guy because you're new, brand new guy. You don't have seniority. Oh, this algebra, this plus, the big seniority. You get president. It's like precedence. It's like a precedence. Okay, it's like multiplication and plus and plus. It's like x plus y multiplied by a plus b. Okay, so this multiplication, it start to distribute. Okay, it's higher order. Multiplication is higher order operator than plus, so it distributes. Okay, so what does this look like? One plus, it's just like a plus b, x plus y times a plus b. Okay, x plus b parenthesis multiplied by a plus b, x plus y parenthesis multiplied by a plus b. Okay, x plus y multiplied by x plus a plus b, just like that. So 1 plus square root of 2 comma 1 plus 2 square root of 2 comma 2 plus square root of 2 comma 2 plus 2 square root of 2 close curly bracket. Okay, I'll zoom it in for you, just for you. Okay, it's like this. Okay, you got it. We have like 17 minutes left, so I gotta wrap it up quick because today's Thursday and tomorrow's Friday, so I gotta get back to work and I gotta eat, and so I'll take a picture and we'll wrap it up real quick. Okay, so thank you for bearing with me. Okay, so yeah, it's gonna be long, long discussion of this expansion algebra. Okay. Okay. So let's take a break, okay? I mean, in terms of this mathematical mumbo jumbo. So I took a picture of this so I can erase this. We'll talk about automata theory, okay? Because it's something I learned in computer science major. Very cool stuff. Turing, Alan Turing, we don't like him, okay? Because he's fucking faggot, okay? So we throw him off the window. Okay. All his theories, we burn it. Alright. It's garbage. Turing fucking complete. Fuck that, dude. We don't like Turing, okay? But automata theory, it did not originate from fucking faggot British Brit fuck fag. No. It's not from there, okay? Automata theory is actually from neurophysiologists or even neuropsychologists, okay? Automata theory. It's like an abstraction, mathematical abstraction of these machineries, okay? So it's like this, okay? Automata theory, because we talked about this, but we didn't quite finish the discussion, all right? All right. So double circle is the satisfactory state, okay? And this arrow coming in is the beginning stage. Okay, I'm just giving you some example. Okay, let's say this is state A and this is state B. Okay, automata theory is something really cool. Okay, we are constructing this automaton. Okay, that recognize even number. All right, so when input is a binary number. Okay, so if input is 0, yeah, then it stays right here. Input is 1, the next number, you have like what? 0, 1, 0, okay? So if input is 1, you go to the state B, okay? And let's say it's 0, 1, 1, 0, binary number, okay? If the next input, we are going this direction, okay? No. Actually, the other direction. From left to right, okay? Let's do 0, 1, 1, 1, 0, okay? Which is what? 2 plus 4 plus 8, 12. Number 12, okay? In binary system, which is equal to in digital system, I mean 10 digit system, what we are familiar with is 2, 4, 8, number 14, okay? Which is an even number, okay? Okay? Alright, so we go this direction from left to right. 0, yeah, you stay right here, you're good. You may be an even number. 0 is an even number, okay? 1, you go here. It's like purgatory, like a prison. Here, Canaan, like land of milk and honey, the promised land, the good stuff, bad stuff, okay? So we'll rename this as good. and bad. Okay, zero, first digit, binary digit, okay, zero. You're a good guy. We want to find an even number. You are even number, you're good. Okay? One, next digit, Boolean binary digit. Oh, you're bad. Okay? One again. Oh, you're bad again. One again. You're bad. You're still in this prison. Now zero. Oh, you repented. The final destination. Yeah, you're a good guy. Because in the end, after all is said and done, in the end, you're a good guy. You're an even guy. Okay, so that's the automaton that recognizes even number. Okay. How about the number that recognize odd number? The automaton that recognize odd number. I guess you just double circle this and single circle this. I guess that's what it is. Okay. Well, yeah, starting point will be probably this guy. Okay, so it's kind of symmetric. Okay. All right. So that's that. Okay. We have 10 minutes left. All right. So I don't have to take a picture of this because this is common sense. Automaton that recognize even number, odd number. That's the very first thing that you learn in computer science, theoretical computer science theory. Okay. Class. All right. What next? We have 10 minutes left. Let's make the best use of it. Okay. So. Because we got a lot to cover, okay? So, all right. So yeah, when you say a plus b square root of 2, okay, you're expanding the universe, right? Well, we better call this x plus a and b. They kind of look like constant, you know. X plus y times square root of 2, okay. You are expanding the universe. All different kinds of numbers that take this form, like a plus bi, or ax plus bx squared, or ax plus bx, or ax squared plus bx plus c. Yeah, like polynomial or imaginary number or this radical composite with rational or real number. Yeah, you are expand by this, okay, you're generalizing. Okay, you're generalizing, okay? X and Y, they can be any numbers. Okay. Alright? But if X and Y, they are just set of 1 and 2, then what is the biggest possible set that we can come up with? The only degree of freedom, only choice, only options that X and Y has is 1 and 2. The biggest universe of that would be 1 plus square root 2, 1 plus 2 square root 2, 2 plus square root 2, and 2 plus 2 square root of 2. It's a Cartesian product concept, exhaustive enumeration using this distributive law. Okay? And to express that is 1 comma 2 plus square root of 2 times 1 comma 2, okay, is equal to 1 comma 2. And using the distributive law in this expansion algebra, square root of 2 comma 2 square root of 2, and using again this brand new expansion algebra concept, there's this distributive law, this hierarchy between the operators. Comma is the set union operator. It's kind of brand new. You don't have seniority. You are junior. You have juniority, okay? But plus, oh, there's algebra. There's thousands of years old seniority. Set union, set theory. Yeah, you have a couple of 100 years old juniority, okay? So yeah, plus wins over set union. Okay, so you start to distribute. 1 times square root of 2. Square root of 2. I mean, not times. Plus. 1 plus square root of 2. Comma. Okay? 1 times, 1 plus 2 square root of 2. Comma. 2 plus square root of 2. Comma. 2 plus 2 square root of 2. That's that, okay? It's just like x plus y multiplied by a plus b. X times a plus x times b plus y times a plus y times b. Okay, it looks just like that. Okay, this expansion algebra theory. Okay, so we're gonna take a picture of this and we're gonna erase it and we'll move on for the 5 minutes left because we want to do the best we can for the time left because we are diligent. We are formalists. We learn from our opposite sex, opposite personality people. Okay, so okay. Let's take a picture of this. Okay, so all right. Yeah, we are diligent. We are disciplined. Okay, and just taking picture. Okay, so all right. We got a long way to go, man. Long way to go. But we got time, so. So yeah, square root of 2, okay? And you have some, let's say, natural number. Set of natural numbers. Like 0, 1, 2, 3, 4, 5, okay? Set of natural number, okay? Natural number, okay? Which is equal to square root. Now we are doing infinite algebra, okay? Infinite set. Is equal to 0, comma, square root of 2, comma, 2 square root of 2, comma, 3 square root of 2, comma, blah, blah, blah. It's an infinite set. Because n, set of natural numbers, is an infinite set, okay? So that's that. But we are also adding n to this. Okay. 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 Then what does this become? It's a just like Cartesian product, distributive law. Okay. It's like let's get rid of zero, okay? Because let's make it easy. Just positive integers, okay? Natural numbers before zero. We don't have any zero in this example. Okay? Yeah, it's like this: 1 plus square root of 2, comma 1 plus 2 square root of 2, comma blah blah blah, comma 2 plus square root of 2, comma 2 plus 2 square root of 2, comma blah blah blah. Okay, it's a complete set. Okay, they express this. It's bye.